going to do today is we're going to start our Chapter 5 notes. We've already kind of done our first Chapter 5 lesson, and that was the other day when I made, okay, let's see, I got to do this now. I got to go over and switch to, hold on a sec. I'm going to, kind of. But we will test them separately, though. Yeah. Okay, hang on. I'm going to have to pause this for a sec. So the diagram we got in yesterday's little lesson that we did in class, where we got a sine curve and a cosine curve, that is kind of the first part of this lesson. So what I'd like to maybe point out to you, guys in the class at home had a little more time because, again, I didn't goof up the measurements, so I went faster. But this, of course, is, this x-axis is theta. It's not cosine theta like it is on the unit circle. In fact, the unit circle would be over here if you wanted it to be over here. One of the animations I told you to watch for homework, we'll watch it together in a minute, actually has the sine curve and the unit circle. But keep in mind, the unit circle wouldn't even look like a circle on this grid because, remember, pi is 3. Right? So there, that distance is 3. So the distance pi divided by 3, 3.4 or 3.14 divided by 3 is about 1. So that's about 1, and this is 1, and that. So this, the unit circle on here would look kind of more like a football if I were to graph it, because I've played with the scale. This scale allows me to see the sine curve very nicely, and of course the blue one is the cosine curve. And what I wanted you to think is, not only can I call this blue curve y equals cos theta, I can also think of it as y equals sine of, oops, I don't need a bracket there, of theta plus, actually I do need a bracket there, what am I thinking? Theta plus pi by 2. Because notice, if you take the black graph and shift it pi by 2 units to the left, it becomes the blue. And this should look pretty familiar to you at this point, because now we're going back to Chapter 1 and our rules on how transformations work. So that was our introductory lesson. Okay, so let me pause my video and go back to my desk here. Okay, there, I'm back to my desk. So if you compare the picture I just showed you that we did on the board to the interactive unit circle that I had you, I put this on the blog on Friday, so you were supposed to play with this over the weekend a little bit. You'll notice that, okay, the green one that I'm doing here is your sine curve. The blue one is your cosine curve. And once again, this one looks very close to the one that I did on the board, right? The shapes may be a little bit different, but it's only different again because of the scale that we're graphing it at. Okay? Just to show you, you know, if I graph a parabola, y equals x squared, I can change its shape a little bit by, for example, putting a number there which makes it skinnier, or a decimal there which makes it wider, right? Or, of course, I could just change the scale. Is going to change its shape. But that's kind of an artificial change of its shape, right? Because I'm just messing with the scale. I'm not really changing the equation any. You've seen this even with things like this back in Unit 1. Remember? You had functions like this, and you were asked what happens if you graph y equals 2 times f of x. And of course, that would be a, what would you call that again? A vertical stretch. Okay. So that's what we're going to be looking at for sine and cosine graphs, is how do we stretch them? Okay. And of course, there's vertical stretches. And do you remember this? If I type in f of 2x, okay, before I turn it on here. how is that one going to change the red graph? Is it going to make it wider or skinnier? It's going to make it skinnier because remember there was an opposite rule at play here, right? I'm dividing all the x numbers by 2. Remember that rule from back in Unit 1? So all these rules from Unit 1 are going to come back, only they're going to come back looking at these graphs, the sine and cosine curves. And again, I have this curve kind of looking this shape because of the scale. This distance here from 0 to 1 is a much bigger distance than, I guess 0 to 1 would be about here, right? The same distance up and down that's 1, back and forth is about 3, right? Because pi is, 3.14 or whatever. If you actually want to see the unit circle and the sine curve on the same grid, I asked you to look at this thing. And there you go. That's the actual size of the unit circle. And notice, it looks like my sine curve is kind of a different, kind of a wider shape. But again, that's only because the scale is different. It's still the same basic shape. It's got a crest and a trough. And these points here that we'd call nodal points, where it's actually the x-intercepts. And that's just rolling the unit circle along and creating the sine curve. So hopefully you guys checked out all of these fun and cool videos, especially this guy. I love this video. Make sure if you didn't notice that I updated the blog on Friday that you maybe take some time in the next couple days and watch all these cute little videos. They're great. And the interactive unit circle is all kinds of fun. And for right now, you can leave that. Let's start formalizing the stuff that we've done just on the board together. First, we have a few definitions. First of all, a periodic function is a function that repeats itself over regular intervals or cycles of its domain. Period is a word that means the length of the interval over which a function travels one full rotation or one full cycle, the distance from one point to that exact same point again. Amplitude is the vertical distance from the horizontal central axis to the, that should say to the maximum or the minimum. Note that the central axis is not always the x-axis. It should say 2. And a sinusoidal function is an oscillating periodic function like y equals sine x or y equals cos x. Both of these things are called sinusoidal functions because they have oscillating periods, which basically means the same thing as this. It repeats itself over and over again. It oscillates. The video that I showed you guys in the blog where they just attach a spray paint can to a spring and then pull a piece of paper, that makes a beautiful sine curve. All right, let's sketch a sine curve. So we're going to work in radians. We could do this in degrees if we wanted to, but it's actually much easier to count in radians along the x scale than it is in degrees. And we'll start with the points 0. We'll just do quarter pies. Pi by 4, 1 quarter, 2 quarters, 3 quarters, 4 quarters, 5 quarters, 6 quarters, 7 quarters, and 8 quarters. And these should be pretty familiar to you. If x is 0, y is the sine of 0, which is 0. The sine of pi by 4 is root 2 over 2. And the decimal on that is about 0.7 approximately. I'll put approximate signs on that. The sine value for pi by 2 is 1. Root 3 over 4 is again this root 2 over 2. Pi is 0. 5 pi by 4 is negative root 2 over 2. 3 pi by 2 is negative 1. 7 pi by 4 is also negative root 2 over 2. And the sine of 2 pi is 0. Cosine, using the same coordinates. Actually, I'm going to do this one in a different color. You've got 2 colors. Switch colors. Pi by 4, pi by 2, 3 quarters, 4 quarters, 5 quarters. Oops, I almost actually wrote 6 quarters. 6 quarters, 7 quarters, and 8 quarters. And that'd be 0. Oh, wait, sorry. That'd be 1. This one's root 2 over 2. This one is 0. This one's negative root 2 over 2. This is negative 1. Negative root 2 over 2. 0. root 2 over 2, and 1. Okay, let's sketch graphs of these things. So can I fit all that? I might have to shrink this a bit so I can fit it all on the page. There we go. Oh, actually, that'll do it. Okay, there. So let's do the black one first. Let's do sine x. So we go through 0, 0. At pi by 4, which is halfway to pi by 2, try to see if you can find the halfway mark, you're going up to about 0.7, which is, roughly 3/4 of the way. And by pi by 2, you make it to 1. At 3/4, you're back to this 0.7 number. And then you're back down to 0. And then here again at the halfway mark, you're back down to this 0.7 or so. And then -1, 0.7, 2. And that is a sine curve. And from here at 0 to here at 2 pi, we would call that one period of the graph. Because look up at the definition. It goes back to its starting point after a period. You might say, wait a minute, it starts at 0. Isn't the first period going to end here at the next 0? No, because notice it hasn't made an entire cycle yet. One entire cycle means it goes up, and then it goes down and back. Okay, let's do the blue one now. Cosine graph. Cosine starts at 1. It actually has the same point at pi by 4. It's 0 at pi by 2. It's -0.7. I think I made that one a little too low. I'm going to erase it and try it again. About the same height. There we go. And then -1. There's another place where they cross. And then there. And then at the halfway mark, we're back up to the 0.7. And then the 1. So and just do your best to make a nice smooth curve. And again, it would continue to repeat like this forever. I just decided to stop at 2 pi. Okay, so those are the graphs that we made on last week with our bicycle wheel. Let's look at some of their characteristics. They are identical curves. The difference is that the cosine and sine curves are translations of each other by a horizontal shift of pi by 2. They are periodic, which means they repeat over and over again. They're continuous. They go on forever. And they're called sinusoidal graphs. The period for each of them is 2 pi, right? The cosine graph's the same. A period would be from here to here, right? So that's exactly a distance from 0 to 2 pi. And here's some of the properties kind of in this nice little chart. The domain for sine of x is, of course, you can go from -infinity to infinity. It goes on forever. But notice the range. It doesn't go ever any higher than 1 or lower than -1. Okay? And the same thing is true of the cosine graph. Where are the x-intercepts? Remember, zeros means x-intercepts? Well, they happen every multiple of pi. All right, let's go back and look at it again. The black graph at 0 pi's, 1 pi's, 2 pi's, 3 pi's, -1 pi's, all of those would be x-intercepts, right? For cosine, cosine hits its x-intercepts at every multiple of pi by 2 that is not a whole number. So at 1 pi by 2, 3 pi by 2, 5 pi by 2, at all the odd multiples of pi by 2. How about that? And then the next one would be over here at 7 pi by 2, and then back here at 1 pi by 2. So that would be all of the places that it hits the x is 0, or that y is 0, x-intercepts. The y-intercept for sine of x is, of course, 0, and the y-intercept for cosine of x is 1. Maximums and minimums happen at 1 and -1. Amplitude is 1. Where's amplitude on these graphs? Amplitude is right here. I'll do it in purple. This height is the amplitude. How high and low does the wave go above and below its x-intercepts? And again, we talked about period. Period is 2 pi. Just for quick sketching, just to one more kind of look at it. Again, start sine x at 0, 0, and then at let's make that 2 pi, and that negative 2 pi, and then we'll make pi right here in the middle, negative pi right here in the middle, and so at 1 and negative 1, what does this thing look like? It makes an entire crest, trough, and back. Right? And then the same thing here. It'll get to its maximum or its minimum at the halfway between at pi by 2. And I don't like that line. I'm going to draw it again. And it'll make its peak at negative 3 pi by 2. It seems to have grown a tumor over here. Oh, having a bad drawing day. There we go. Good enough. And then cosine. Let's put the same grid on it. 2 pi there, negative 2 pi there, which means halfway is 1 pi, and halfway is negative 1 pi, and then that's 1 and negative 1. Cosine starts at 1, right? And then it would hit 0 at the halfway mark, and it would be down to its minimum there. So down, and then it would hit the 0 halfway again, and it would be up to its maximum there again. I think I just made that higher than the other one. I didn't mean to do that. There we go. Something like that. And then, again, it hits 0 at halfway. It got to its minimum at negative 1 pi, halfway at negative 3 pi by 2, and back up to its maximum there. So. Don't fret if you're not great at making these diagrams. Notice I'm a little clumsy at them myself sometimes. Okay. Like every other kind of graph we've talked about this year, we have to learn how to do transformations on it. So the first transformations we'll look at will be two that we're fairly familiar with. I guess we used to call this A, the vertical shift. Or vertical stretch. Sorry, I meant to say the word stretch. We used to call A vertical stretch. We used to call B horizontal stretch. Now we have fancy new words for them. A, this is kind of helpful, stands for amplitude. Formerly vertical stretch. And the B is the value we use to calculate period. B value is not period itself. It's what we use to calculate period. And again, what in the old unit, formerly known as horizontal stretch. Here's the actual formulas for the two letters. Amplitude is just the A value. You take the absolute value of it because amplitude is just a distance on a graph. It doesn't make any sense in this context to call distance positive or negative. And B is used to find the period using these formulas. If you're doing a graph in radians, you'd use the formula on the left. And if you're doing the graph in degrees, you'd use the formula on the right. Notice that B is not period itself. It's used to find period. So what would this graph look like? Y equals 1/2 sine of x. Okay, well, once again, I'm going to take the graph and split it in the same way we did the sketches on the last page there. 2 pi, pi, negative 2 pi, and negative pi. And this will be This will be -1, and this will be 1. Now, just like we did back in Unit 1, maybe it'd be helpful to have our parent graph on here, right? So our parent graph was, let's see, goes through there, and it hits its peak at pi, and it's back down to 0 here, so it did that, right? Oh, wait a minute, sorry, whoops. Sorry, no it didn't. That's 2 pi, not pi. What am I doing? Oop, sorry. It makes its peak at 90 degrees, or pi by 2. There we go, and then it's back to 0, back to -1, back there, that's it. Sorry, I forgot that I was counting in 2 pi's, not pi's. So there's my parent function. And then on the negative side, again, its minimum would be down here. And its maximum would be halfway here. There. There's our parent function. What does the 1/2 do to it? Well, the 1/2 shrinks the amplitude. Right now, this amplitude, this distance here, can you see my cursor? Yeah. This distance here is 1. Well, now that distance is going to be 1/2, right? All y values multiply by 1/2, which is the same thing that number did back when we did transformations in Unit 1. So this point is now here. This point's still 0, right? So it's going to do that. Instead of being down here at -1, this point's going to be -1/2. And again, multiplying 0 by 1/2 doesn't change the fact that it's still 0. So this -1 is now -1/2. And this height of 1 becomes a height of 1/2. There we go. Okay, I'm going to have to change my scale for this one. I'm at cosine. I've been doing cosines in blue, so I'm going to go back to blue. So for this one, I'm going to have to actually go 1, 2, 3, and 1, 2, 3. And I'll keep the horizontal scale the same. So that's 2 pi, -2 pi, halfway is pi, halfway is -pi, and okay, well, this distance here and this distance here should be the same. They kind of don't look it, but oh well, it'll be close enough. Okay, and let's see, what do we know? We know our parent function starts at 1, and at pi by 2 it hits 0, and at pi it's down to -1. These are negatives, I forgot to write the negatives on them. So it's down to here, and then it's back up to 0 here, and then back up to 1 there. So there's our parent function. Again, notice how this one looks a lot flatter than the one to the left here, but that's only because I changed the scale. I had to. I wouldn't have fit an amplitude of 3 in if I didn't change the scale. And this is where it's going to hit 0, and then it's going to go down to -1, and then back to 0, and then up to 1. There we go. And now let's draw what happens here is that all y values multiply by 3. So this 1 is now a 3. This 0 is still a 0, because 0 times 3 is still 0. This -1 is now a -3. This 0 is still a 0, and this 1 is now a 3. And again, once again, I have kind of a wonky line that I feel like I want to erase a little bit. Oops. There we go. And over on this side, this 0 is still a 0, but this -1 is now a -3. This 0 is still a 0, but this 1 is now a 3, because they all got multiplied by 3. I don't know about you, but I almost find that when I draw a little faster, I tend to make a straighter line or a smoother curve. The more I slow down, the more wonky it gets. There we go. Now, careful. What are these ones doing? Okay, tell you what. I'm going to put my parent function down. I'll go back to the original scale that we did in the first place, 1 and -1. 2 pi here, -2 pi there. Halfway, I'm going to try to measure halfway a little better. There, is that better? Pi, and is that better? -pi. Okay, what's the parent function doing on sine again? So the parent function is just y equals sine x, which goes through 0, 0, 0, positive, negative. There. Right? That's what it does. Oh, might as well finish it on this side. Negative, 0, positive, 0. Oops. Oh, I went right over it. There we go. There's our parent function. All right. What do you think? What does the 4 do? The 4 divides all x values by 4. And what you could say then is, this is my b value, so b is equal to 4. And go back, we have this fancy formula here. Period is 2 pi divided by b. So, come on, move you. There we go. So period for this graph, I'm just going to work down here if that's okay. Period for this graph is equal to 2 pi divided by the absolute value of b. Now, b here is a 4. Absolute value of 4 is just 4. Now, you got to be able to recognize when you can simplify fractions, right? I'd never say 2/4 when I could say 1/2. Do you realize what this is telling you? This is telling you, so the graph makes an entire cycle in pi by 2, not in 2 pi. See, my normal graph makes an entire cycle, right? Start, make it to the top, make it to the bottom, and back. How much distance did that take horizontally? 2 pi of distance. If you're in degrees, it took 360 degrees. How much will it take now? It'll only take 90 degrees. It'll take pi by 2. In other words, where there was 1 of these things, there is now going to be 4 of these things. So this is going to be kind of hard to draw. I will have to kind of split this up. This is pi by 2, right? I'm going to have an entire finished crest and trough oscillation between here and here. So I guess at the quarter mark, I'd make it up to here. And then at the half mark, I'd hit a 0. And then at the quarter mark, I'd be there. So here we go. There we go. So there's 1. 2. 3. Oh, geez, I just missed that. 3. 1, 2, 3, 4. So 1 complete, 2 complete, 3 complete, 4 complete. There we go. Then I got to do the same thing on the other side. So let's see. There is pi by 2. I have to have a complete crest and trough done by then. So that means I have to have a 0 there and a 0 here, which means I go down and back, up and back. There's 1, 2, 3, 3, and 4. There. Notice I tried really hard not to go higher or lower than I was supposed to. But there we go. We'll take a look at this on Desmos. It'll be a better drawing than I made. All right, back to blue. What's the cosine of x divided by 2 going to look like? Well, now we are doing what? Think of this as, if you like, the cosine of 1/2 times x, right? So that means we are dividing all x values by 1/2. And if you divide by 1/2, what mathematically is the other way to explain what you're doing to a number? You're timesing it by 2. Right? And now for this blue one, period, so for this one, period is equal to 2 pi divided by the absolute value of 1/2. It's a positive number anyway, which is equal to 2 pi divided by 1/2 is like saying 2 pi times 2 over 1. That's how you divide by fractions, which is 4 pi. So this graph needs 4 pi to make 1 period. So it will not make an entire cycle in the graph that I'm looking at. So let's stick to the same grid dimensions that we had on the one on the left and the one above it. So if this is 2 pi, this is negative 2 pi. This is 1. This is negative 1. This is pi. About halfway, that's negative pi. And okay, what does cosine do again? Cosine starts here, and then it hits a 0 at halfway at pi by 2. Right? And then it's at its minimum down at pi, and it crosses again at 3 pi by 2, and then it makes it up to here. And okay, that's really wonky this time, but you get the idea. I guess that blue line's kind of in the way. There. That's my parent function. What's my new function going to look like? It's going to be way wider. Notice timesing 0 by 4 does not change anything, or sorry, timesing 0 by 2, I mean, doesn't change anything. So this point will stay the same. But this point here that was pi by 2 got multiplied by 2, so now it's over here. And this point here moves over there. So it's actually way wider. Wow. That should start curving up there. You get the idea. And then this point here moves over to there because it's been doubled. And then this point here moves over to there because it's been doubled. So let me get this blue line out of the way. There we go. Okay, I wish I could draw prettier than that. Let's take a quick look at Desmos. And this will also show you how to actually use Desmos to do these things. Desmos can graph trig just the same way it graphs everything else. Why is this not opening? Come on, open. Fine. We did. Geez. Okay. All right, let's get rid of all these graphs. Don't need those. Okay, so let's see. We want y equals the sine of x. And okay, check it out. There we go. Let's make this look the same as mine. So what we can do is we can go to the settings here, and we can actually say that our x value, we can actually count in pies. This is kind of cool. Desmos knows pi, so watch this. You can go -2, and then when you want pi, just type in pi, and it'll go pi, and it'll just change it to pi for you, and then delete that other 2 there. There we go. And then for the other side of the x-axis, we want 2, and then type pi, and it knows that that's pi. And what did we count our steps in? We counted in pi by 4s. So we can do that on here too. We count in steps of pi divided by 4. For the y-axis, well, let's see. We only really needed to go from -1 to 1. And notice as soon as I started typing in pi's, it knew that I was in radians. If I wanted to switch to degrees, I could. But degrees are bigger numbers. So there we go. There's the graph. And okay, what did we graph for sine? We also graphed y equals 1/2 sine x. So y equals 1/2 sine x. And there we go. Compare that to the notes we just did. And the other sine one we did was y equals sine 4x, which doesn't make it any taller or shorter. It just squooshes more cycles in. So y equals sine 4x. Ah, that's much prettier than mine. But there we go. So there's all the sine ones. Now the cosine one, so let me just change that. Oops. For the cosine one, can't spell cosine apparently. There we go. For the cosine one, we decided on the second example that, well, if we're going to put a 3 here, we're going to have a higher scale. So that's real easy to fix. You just go to here and change your y-axis from -3 to 3. I honestly don't mind if you use Desmos to help you with the homework, right? If you're getting stuck on drawing these graphs, use this to help yourself out. Eventually you have to be able to make it without them, but when you're learning, this is a good tool. Okay, so now it was y equals 3 cos x, right? Compare this to our notes. Pretty good? Check this out. Instead of calling this y, suppose I called it f of x. Because then I could use function notation and say y equals 3f of x. Oh, remember function notation from Unit 1? And then the last example, we decided, we went back to the original graph dimensions, right? So get rid of that guy and go back to, I'll just stretch it. There we go. There. And we went back to, and of course we only went to 2 pi. Oh, that's close enough. That is almost 2 pi. There we go. About there. Okay, so that was the dimensions on the last one. Only the last one was 4. Y equals, oops. Oh. Wow. Sorry. There. Y is equal to cosine of x divided by 2, which again you could write as y equals cosine of, and then you need a bracket for this so that it knows that all of this is the angle. Cosine of, and you could actually type it as x divided by 2, the same way that, actually I guess I got an extra bracket there I don't need, there we go. Or you could type it the way that we kind of thought about it, cosine of, open a bracket, 1/2 x. Notice that it's green, it's purple, it's green, it's purple. Or again, we could just go back and use function notation. Y equals f of x divided by 2. Right? It's purple, it's black, it's purple, it's black. All those things say the same thing. Okay, cool? So there's how you use Desmos to help you. And there's our introduction to sine and cosine. We're actually going to jump now. The next page in your booklet isn't 5.2, it's 5.3. Tangents is weird. Okay, I'll come back to this graph. Maybe I'll just kind of close these. I like where the scale is right now, so I'll leave it there. And go to the next page, and it's tangent. Now remember that tangent is sine divided by cos. and that tangent of theta is the slope of the line through this point. Now think about the slopes of this thing. What is the slope right here? This looks to me like it's 45 degrees, aka pi divided by 2, or pi divided by 2, pi divided by 4. What's the slope right here? Well, it looks to me like the slope here, rise over run. What do you think? What's the slope at that point? How much does it rise? How much does it run? What's the slope of that tangent? Or what's the slope? So the slope of this would be, the slope of that would be the negative reciprocal of the slope of this. So this slope to me looks like it's about -1, which means the slope of this is +1. Right? So that's why the slope, the tangent of pi by 4 is +1, because that's the slope of this radius line. Now imagine as you go around here, as you get to this point here, a tangent at that curve is going to have this for a slope, so that means this line here would have a very tall slope, like this is a really big number. And if you actually made it right to the top, think about this slope. It becomes infinite. By the same logic, if you go down to here, well, the slope of this line is infinite, which means that the slope along here, slope from there to there, is 0. So here's what happens when you're doing tan. I'll do this one in a different color. I'll do this one in green, let's say. There we go. So using the same points, 0, 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, and 8/4. So using those same coordinates, what does tangent do? Well, the tangent of 0 is still 0. The tangent of pi by 4, kind of as we saw up there, the tangent would be the tangent of this line here. Rise over run should be the same thing. So 1. And isn't that true? Isn't the tangent of pi by 4 1? Because it's √2/2 divided by √2/2. And the tangent here... Oh, question?
Why is there a 5 pi divided by 6?
Oh, because I wrote the wrong number down. Thank you. That should be a 4. I'm counting in quarters, not 6. Thank you. So now, back here, think about at 90 degrees. Rise divided by run. Well, I rise 1 unit. How much do we go back and forth? 0. What's 1 divided by 0? Undefined. You can't divide by 0. So this is undefined here. At 3 pi by 4, you're at -1. At pi, you're at 0. At 5 by 4, you're at 1. At 3 pi by 2, you're again undefined. At 7 pi by 4, you're at -1. And at 2 pi, you're back at 0. So this thing here is going to look like this. It goes through 0. By the time I'm at, let's see, what is it? Pi by 4, I've made it up to 1. And then, kind of like it shows here in this thing, as I move this radius arm further and further that way, the slope gets higher and higher until it actually kind of becomes infinite. So it actually kind of makes a weird curve like that towards infinity. This is meant to be a much smoother curve. And then at negative pi by 4, it would again be -1. And it would head towards infinity. I am drawing these really badly, I've just realized. Okay, anyway. Oh, hang on, is this pi? Oh, I'm very much drawing it badly. Sorry. Can you erase that? I'm sorry. I thought this was pi by 2. My eyes are fooling me here. Sorry. At pi by 2. Here, let's draw this so I don't goof this up again. Back in grade 11, you called that an asymptote. So at pi by 4, there's pi by 4. You're at 1. So there we go. So I can make that a little bit like that. And then at negative pi by 2, again, this is an asymptote. It will head towards infinity, but it'll never reach it. I like the left side of that curve way better than the right. I made this part here too straight. Let's see if I can do better on this one. This will be 0 again. And it heads towards 1 at pi by 4, and then it heads to infinity. And then another asymptote here, because at 3 pi by 2 we're undefined. And then again at pi by 4 we hit our 1, and that's the best one yet. That's pretty good. I like that curve. Somebody in my other class actually saw this and went, oh, those look like cubics. They kind of do, but they're a little different than a cubic curve. I'll show you on Desmos. Again, we can make more of these. Here, let's try one more. 2 pi, at the quarter mark we hit -1, and at the next quarter mark we hit +1. Okay, let's see if I can make this. I made that part too straight again. Anyway, just do your best. And let's show you what it looks like on Desmos. Let's show you what it looks like when a professional does it. Where are you, Desmos? I don't know why this doesn't work when I push on it. There we go. Okay, so y equals tan x. See how they look? And as I zoom out, it's not letting me zoom out. Let's just go to home maybe. Will that help? There we go. You can see the curves get more pronounced the more you look at it at kind of a taller scale. That's what I was going for in my diagram. Although, again, when you're only down at 1, again, zoom in, when you only have a scale of 1, it doesn't look very curved. But when you have a scale, when you have a scale more like that, you get more of a curve. And if I were to graph just x equals pi by 2, by 2 it says, that is, as you can see here, I'll make that a dotted line. Dotted line, where's my dotted lines? There we go. Dotted line, there. Oh, yeah, that worked. As you can see, that's an asymptote, right? If I move my scale, I know it's looking like, well, it's going to cross it. Actually, no, it won't. If I zoom in, there will always be space. I could zoom forever, and there will always be space. I'll get infinitely close to that number, but I'll never actually reach it. And again, you saw that concept back in grade 11 when you were doing asymptotes. Okay? So that's tangent. What kinds of things can you say about tangent graphs? Well, their domain is x is an element of all reals, which means x can be any number, except x can't be any odd multiple of pi by 2. So x can't be 1 pi by 2, or 3 pi by 2, or 5 pi by 2, because again, that's the places that we get these asymptote lines that it'll never touch. See, that's 1 pi by 2. That one there would be 3 pi by 2. Over here would be 5 pi by 2. You get the idea. Okay? What else can we say about tangent graphs? Well, they do hit every y value possible. Y values can go from -infinity to infinity, and they have x-intercepts at every whole number of pi. 1 pi, 2 pi, 3 pi, 4 pi. You cross the x-axis. The y-intercept happens at 0. The period is pi. Take a look at that. You can kind of see it in the graph. You can do one of these entire lines between -pi or -pi by 2 and 1 pi by 2. So the distance between, say, here and here, where you'd fit an entire arm, one whole cycle, that's a distance of 1 pi from there to there. Here, let me put another border line on here. And once again, I don't like that. It's an asymptote. It should be a dotted line. There. Between these two dotted lines is the same distance as it is from 0 to pi, right? So it's a period of pi. You finish an entire crest or entire downward arm and upward arm. And again, people were saying, isn't that a cubic graph? It's similar. It's just not quite the same. Can you see that? There's y equals x cubed. It's a little different. It's actually got a direction change here that a tangent graph doesn't have. So it's a little bit different. Okay, what else do we know about tangent graphs? They have asymptotes. That's one of the few things you'll ever get asked. We're not going to actually spend a whole lot of time transforming tangent graphs. But we might ask you a question like, hey, where's its asymptotes? Like, for example, let me go back to the graph here. This one has asymptotes every pi by 2. But what if we just shifted this over? Well, say we shifted it over by pi by 2. Say I go plus pi by 2. Notice it just shifted everything up. What did that do to the asymptotes? Well, actually, it didn't do anything because I shifted it up. So that's still the same. But what if this pi by 2 was inside here? Now, that's not the asymptote anymore. The asymptote has to move over by the same amount. The asymptote's now at pi and negative pi. Get it? So that's about all we'd ever ask you to do with tangent graphs. Basically draw the shape, and if we did a very minor change to it, like shift it left or right, tangent graphs don't look much different. Let me go back to what I had before. There. Tangent graphs don't look much different if you stretch them. Here, watch. We'll make all y values doubled. Not a huge difference. All right, tripled. Quadrupled. Notice that if I just change the scale, it doesn't even look any different than it did when I started. So, we don't tend to worry about stretching tangent graphs too much. And notice that doesn't change where the asymptotes are. It just changes how high you are when you start to get really close to it. That's all it changes. Okay? So tangent graphs are not the big deal. The big deal is back here. Sine and cosine graphs. Which, why is that not coming down? Oh, there we go. There we are. Sine and cosine graphs, these guys. These are the kinds of sketches that you're going to have to be able to make. And your first homework actually has some. So, okay, I'm going to stop the video here and hand out some stuff for people to do.